Here we are again, still working on light, Corona video, number 10. Still talking about lenses. Now moving the object in front of the focal for a converging lens at BHS. The Dartmouth of the MVL. Alright, so here we go. Let's start by building our x-axes again. So here comes my x. Get my ruler lined up. That one's about ready to retire. Alright, then we'll put in our y-axes here-ish. And we're going to say this side's positive and this side's negative. Now I'm going to draw in my converging lens. Remember, converging lenses are skinny on the end and fat in the middle. Not the best lens I ever drew. Okay, and then let's do some givens. So what am I going to give you in this problem? Well, I got to give you focal. So what's my focal? 5. Same as before. What's my object distance? Let's do 3. What's the height of my object? Also 3. So these are things that will be given to you. Givens. So we can start to plot things now. Remember, lenses have 2 focals. So I'm going to count over 1, 2, 3, 4, 5 focal. This is the one we're going to use for math. 1, 2, 3, 4, 5 focal. This is the one we use for ray tracings. This time around, the object is located 1, 2, 3 away, and it's also 3 tall. So it looks a lot like that. And we're ready to do some tracing. So remember, we don't really ever deviate in our ray rules. The ray rules don't change. So first thing we're going to do is work on how we come in and how we leave. Let's come in parallel. This one seems to never change, right? Come in parallel, turn your ruler, line it up with the positive focal. Yikes. Keep on going. Okay? Then we're going to do it for the second ray. We're going to go focal parallel. So we're going to take our ruler, line it up with the focal point, depart, hit the lens. Notice how I did that, okay? For all of you that struggle with where do these lines come from? I'm lining up with the focal on the top of the arrowhead and coming into the y-axis. Then I'm going to turn and leave parallel. Parallel to what? Parallel to the x. Notice these rays are not going to intersect on the positive side. This is a hint. Virtual. You will have to do some dotted lines or ray trace backs to figure out where it would intersect. Third ray rule. We want to go to the origin. Here's the origin. From the top of the arrow, and then guess what? It's the only flat part of the lens, so it keeps on going. Everything else is curved. Here's the only flat part. Whammo. Origin equal angle. Keep on going. So what do we do now? Well, we trace it back. We trace it back to see where the rays would intersect behind it virtually. It's my first. It's the refracted rays that we're tracing back. I'll do it for this one as well. Come on back, y'all. Okay, and then we're going to also do it for this dude here, ray 3. Ooh, look at that. Lining up nicely. There you go. So that's that intersection point will give you an idea of what it looks like when we look into the lens. When would you want something to look bigger like this? Well, what about a magnifying glass? What's the purpose of a magnifying glass? Well, it's not to project it onto something. It's just so when you look into the glass, it looks bigger. So here we have a virtual, I'm going to describe it, virtual, erect, enlarged. These are our three describing words for the image. Let's go ahead and write some stuff down about our graph, counting boxes. So, graph results are as follows. The distance to the image, let's count. Here's 0. Here was 3, 4, 5, 6 and change. Let's say 6 1/4. 6.25. And it's negative because it's on the negative side of the lens. And look at the direction of the rays. They're going to the left. Therefore negative. Big problem for people trying to understand this. Why is DO positive? Why is that negative? Height of the image. 1, 2, 3, 4, 5, 6, 7. 7. Height of image 7. Distance to image negative 6.25. Magnification time. It's a fraction. We want to compare the height of the image 7 to the height of the object 3. 2 and a 7th. How about that? Times 2 and 1/7 or 1/3. 2.33. 2.33, and it's positive, meaning it's erect. So our graph results are matching our describing words, which is always good. Now we must math. We must. So when we math this, we use our two formulas. And those would be magnification and lens makers. So let's get to these two formulas. 1 over f equals 1 over di plus 1 over do. Let's put in our knowns. That's the yellow thing right here, the post-it note. 1 over 5 converging positive equals 1 over di plus 1 over 3. And you're like, wait, the object's on the negative side of the lens. But remember, it's all about the direction of the rays. So it's actually positive. Do will always be positive. Check it out. All right, so now we find a common denominator. Well, 15 is the obvious one, so we'll say 5/15 and 3/15 equals 1 over di plus 5/15. Subtract, so we end up with a negative number here, giving me negative 2/15 equals 1 over di. Therefore, di is going to be equal to negative 15/2, which is the same thing as saying 7.5. Whoops. Looks like I was off a little bit. So, how far off was I? When I did it before, I said it was negative 6.25. Turns out it was actually negative 7.5. Now let's find the other things, like magnification. So remember, magnification has its own formula, hi over ho, but it also equals negative di over do. So I'm going to put in negative of a negative. Negative of negative 7.5 is positive 7.5. The distance to the object, do, was given 3. Now we can use this to find our magnification. Notice the negatives cancel and we'll be left with a positive. So 7.5 divided by 3 is 2.5. So my magnification is times 2.5. What did I have? Let's take a look at what we had from our graph. We had 2 1/3. Pretty darn close, not too shabby. Definitely ballpark. All right, so then we use this magnification and we set it equal to the other part, which is hi over ho. This time we fill in ho with the given 3. So we're going to take 3 times 2.5, which would be 7.5. So this would be hi, 7.5. How'd we do there? Our graphing answer was 7. Not too bad. Definitely close enough. Close enough. Now let's check our math answers and make sure that they match our graph answers. Well, DI is negative, and that's why it's virtual. And it's erect because the sign of HI is positive. Okay, matching up. And then it's enlarged because HI is greater than HO, but magnification tells a real story, and the magnitude of the magnification is greater than 1. And there you go. There you have it. Our second example of converging lenses. Now, next time we meet, we'll be talking about the other type of lens, diverging lenses. And we'll talk about what those can be used for, and we'll talk about the math and how the focal is negative. So, till next time, keep up the good